Okay, let's do part 2 of the Stokes theorem. Yesterday we took flux and we turned it into a line integral, and we used a parametric technique to find the line integral. What Stokes theorem says is you can use it the other way around. Suppose you want to find this line integral, f dr, then you can turn it into a flux, but actually the guy that you use is this. Can you remember this weird ugly guy before? You remember this formula with the P, Q's and R's in it? Right. So that guy we have done before, right? So all we're going to do is use it to find the line integral. So what does it essentially says is if you're doing the line integral over a curve C of some vector function f with respect to its the derivative of its position function, which is essentially what that is, you are looking at a double integral over an area D of this expression dA, and dA is either going to be dy dx or r dr d theta. F is going to be P, Q, and R, which it always is. And Z, basically what g of xy is, because you need to know it for these two terms, is going to be the surface of S. So you've got a curve in 3D. Think of a surface. That surface is then going to generate a D, and it's going to generate a g of xy. Phew. So what does D look like? So can you imagine this is the curve C? If you project a curve onto the floor, so this is basically a line integral, right? So it's actually going up and down in 3D, right? You know, it's like beveled at an angle, right? Zigzagging up and down. But if you imagine that projecting to the floor, do you see that you would generate a region, the green region D? It's an area D. So there's a lot of pieces to this puzzle. So I think the best way, in a lot of situations, is by examples and show you how you apply that process. So what we're looking at right now, just getting my windows sorted out here. There we go. What we have right now is we're being asked to find this fella. In fact, questions 8 to 15, they're all going to ask you to find this line integral, and they're going to tell you who F is, and they're going to tell you who C is. And from that information, we are going to get this guy here, and whatever he is equal to, it's the same answer as the guy you're really looking for. Well, let's see, what do we know? We know that C is the triangle that you get when you do 7, a 7, and a 7. So I'm assuming then that this here is basically our surface, and that C is what you get when you go around that surface. So what do I need from that information? I need to know what this guy looks like when you project it onto the floor. Now you can imagine that you've got an X, your Y, and your Z axis. But when you project this thing onto the floor, do you see that you just make a triangle that looks like this? And this here is the D that we need. So I'm going to work on how I would do a double integral of this region here. Well, I guess I need to do a little bit more work. Would you agree that this straight line has equation 7 take away x? Are you happy where 7 take away x came from? Can you imagine finding the equation of that line? So that means I could set up what region D looks like. It's x going from 0 to 7. And it's y going from 0 to that straight line. And that's one piece of the puzzle fixed. So do you see, I now know what the limits of integration are. It's going to be from 0 to 7 and y equals 0 to y equals 7 minus x. Now, do I know P, Q, and R? Well, that's an easy one. That's P, that's Q, and that's R. So I'm good with that bit, and that bit. What I'm not good with is I don't know who G is. Now, G is basically the surface. So I need to find the equation of that triangular surface. Now, I'm not just going to get the triangle, but can you imagine the entire surface that that would generate? Which means, don't I need to find the equation of a surface that passes through 3 points? You know, like 2x plus 3y plus 4z equals 10. Now, we have done that before, but let's remind you what we know. I'm going to call this guy P. I'm going to call the second point Q. And I'm going to call the third point R. And I want to find the equation of the plane that passes through those 3 points. Does anybody want to start the ball rolling by telling me what I need to do just to collect the information, what I would do first?
You need to find vector PQ and PR.
So this is quite time consuming, but it's not difficult, right? The numbers are really nice. So I'm just going to do the, second take away the first, 0 take away that guy, -7, 7 take away that guy, and 0 take away 0. So that's the first one. And to do PR, it's going to be 0 take away 7, 0 take away 0, and 7 take away 0. It's going to be that guy. So that's pretty much like me doing, that guy and that guy. So we've got a P, we've got a Q, and we've got an R. So where do we go next? Remember, the goal is to get the equation of a plane that passes through 3 points. Think Calc 3. What would you do next?
Cross product?
Yep. So we're going to go what's called the normal to that plane, and it's found by taking the cross product of these two guys. And the cross product, we've used that in other situations, but in this situation, it's all done with numbers. -7, 7 and 0, -7, 0 and 7. And the cross product is so many i's, take away so many j's, plus so many k's. So here goes. If you cover that guy up, you get 49 take away 0. If you cover this guy up, you get -49 take away 0. And if you cover this guy up, you get nothing, take away a negative, so you get add 49. And so, oops. We get 49. Two negatives make it 49. 49. And then we do the dot product, and it's going to equal the dot product with any guy you like. So I'm picking the first one. And let's try that again. I'll do it with the first one. So it's position vector of P, essentially. So I get 49x, 49y, 49z, and basically dot product of that is whatever 7 times 49 is. So I can get x add y add z equals 7. Does that look, you know what my accountant's like, does that look okay? Right, of course, a minor rearrangement. That there is our g of xy. And that's the guy that we need in order, I can find my little guy, in order to go here, here, and here. So we have all the pieces that we need. Just put that there for a second. So I'm going to find this double integral of the region D, which is this guy here. We're going to do it, oops, using negative p dg by dx, take away q dg dy, add r, and I'm going to do dA. Right, that's the general version. Now I have all the pieces here, so let's take them as I need them. This is going to be from x equals 0 to x equals 7. Then it's going to be from y equals 0 to y equals 7, take away x. It's going to be negative p, which is negative of that guy, times dg by dx, which is what do you get when you differentiate this with respect to x, and the answer is -1. Take away q, which is this guy, times dg by dy, and if you differentiate this guy, you get -1 again, plus r, which in this case is z plus x squared. Put a bigger bracket around everything. Yikes. Okay, very squeezed in dx dy. There is something missing here, or something that needs to be changed. Can you see what it is?
All the z's should be 7 minus x minus y.
Yeah. So this fella is going to be negative times that, that's a plus, so I'm going to get that guy. This guy is a negative and negative, so I'm going to get that guy. And z plus x squared is going to become this guy plus x squared. And I'll have a quick look around. I guess there's a little bit of fixing, but really it's hardly worth it, but I'm doing it now. That guy kills off that guy, and that guy kills off that guy. And it looks like I'm left with x squared plus y squared. I forgot somebody. Arr. Do you see how I forgot to change? It's not meant to be this long. That guy squared, got x squared taken care of, y squared taken care of. This guy plus 7, right? I'm getting very close to the ... stage. Can you imagine that I foil this horrible mess out? Isn't that basically just a good old-fashioned double integral that'll take you another 5 minutes to do? But pretty much the question's over. Now, do you see how this is a little bit more awkward because you have to do all sorts of things before you can actually start using this formula? And the things that you've got to do are, in particular, you've got to figure out who D is, right? The projection of the curve onto the floor, right? You've got to figure him out. And you've got to figure out who G is, the equation of what the surface would be. And once you put the whole mess together, then it's maybe quite big and cumbersome, but it's pretty straightforward. Well, that one was quite long. And the good news is the next one's going to be a lot quicker. And this is like 10. So what we got here is find a line integral. This is going to be your vector function. And C is the part of the plane, that's this part of the plane, that is in the first octant. Now, the good news is they've already told me the equation of the plane, right? So I don't need to go through that PQ, PR, cross product stuff, right? Don't need to do that. This fella here then, will get us the g of xy that we need. And it's simply just now, wasn't that a lot nicer? Okay, got that guy. Now it's a little bit harder, but can you imagine that you've got your curve and it's doing whatever it is doing up there? You're going to project that onto the xy plane. It's going to create a D, right? So we have got to figure out, what does this thing look like if you project it onto the floor, but you restrict it to the first octant? So this is going to be what D looks like. Since it's in the first octant, doesn't that mean it's only going to be positive X and Y? Since it's projected onto the floor, doesn't that make Z equal 0? Great. Z equals 0. So what does that look like? It looks like the straight line 3x plus 2y equals 1. Because when you make z 0, don't you just get 3x plus 2y equals 1, which I'm assuming in this fella here, right? Now, I probably would like to rearrange it a little bit. So it's a half, take away 3 upon 2x, so I guess that's a half. And it slopes down to the bottom. What's it going to be when it hits the bottom? It's going to be, well, that's going to be 0, so I guess this is going to be a third. There is the D.
Mr. Robertson, sorry,
Yes.
but I have to leave.
Okay, well, thank you for telling me that. Right, are we okay about how we constructed the region D from this information here? Right, can you imagine as the plane cuts through the first octant, it basically leaves a little triangle which projects down to the floor and looks like that. So we are going to set up D, and it's going to be x equals 0 to 1/3. And the y value is going to be from 0 to that guy. So there's D. Do we know G? Yep. We're always going to know P, Q, and R. Once you know those three things, you're ready to do the question, right? You're ready to answer it. So this particular line integral is going to be this double integral. Now, start putting the pieces together. Start over here, give myself plenty of room. X is going to go from 0 to 1/3. Check. Y is going to go from 0. If you're wondering what I'm doing here, I didn't really put it in here, but aren't I doing the little vertical rectangle thing? So it's going to be 0 to 1/2, take away 3 upon 2x. Negative P is negative 1 times, if you differentiate this fella with respect to x, you get negative 3. Then you subtract Q, which is that fella, times derivative with respect to y is negative 2. You then add an R, which is that guy. And I'll do a dy dx. So that's going to be this fella again. Y equals 0 to 1/2, take away 3 upon 2x again. These two guys get me 3. This guy times this guy gets me 2. So that's 2x plus 2yz. And this guy here is just left alone. So that's going to be plus an xy, take away a square root of z. And if you're better than I am, you would probably do these 2 lines in one go. But essentially, won't I replace that z and that z by this? So I now have 3 plus 2x plus 2y times all of this, plus an xy, take away the square root of all of this. Oh, I think it's time to dot it again. For the most part, it's just going to be a polynomial. I think the awkward one's going to be integrating this square root, right? Because we're going to have to integrate with respect to y first, this square root. Great, now that's not going to be particularly pretty. So let me just isolate that question. Suppose I wanted to integrate this fella with respect to y from y equals 0 to there. Well, square roots are not very helpful if you want to integrate, so I'm going to call it a half power. And then I'm going to just basically integrate it the way I would. I'm just going to think of that x as being a number. It's a constant. So the rule is add 1 to the power. Divide by the new power. So far, so good. But don't we have to take care of the -2? And what do you do with that -2? Well, do you divide by -2 or do you multiply by -2? I guess that's the choices. Can you remember?
You divide.
You divide, which is another way of saying -1/2. So what you're going to get here is -1/3, 1 minus 3x minus 2y, all to the power of 3/2. Then you plug these guys in, and that'll just turn into an ugly version with x's in it. So it's pretty time consuming. Lots of places for little fractions to disappear on you. And you do 90% of it right, but you still don't get the answer. Any questions so far? You see, essentially, aren't we just doing the same thing, different situations, but aren't we trying to find out who little g is, who d is, right? And PQ now. Here's another one. This is like question 11. Okay, let's look at what we have here. C is the part of this surface that's in the first oct. Well, great news. Haven't they told me what G is? Right, the surface. Now, when you put it on the first octant, don't you make that 0? Right, that's the floor. And don't you only focus on what does that guy look like, which is 1 minus x squared minus y squared equals 0, right? What does that guy look like in the first quadrant? Well, if I rearrange this, don't you have a circle? But if it's in the first quadrant, don't you only have that piece of the circle? Would you say that this would be a good candidate for the RDRD theta version? And so this is going to allow me to get D. I'm going to say that R goes from 0 to 1, which is the radius. And I've got to be a little bit more careful. Doesn't theta only go from 0 to pi upon 2? We're comfortable with that. So I got my Z, I got my D, and I got my PQR. So I am ready to go. Right, ready to start using this guy. So the line integral that we're being asked to find is going to be the double integral of this guy we got that guy. Okay, so here's all the pieces I need. Let's see what they look like. Shouldn't really matter, so I'm going to do theta equals 0 to pi upon 2, r equals 0 to 1, bracket. Negative p is negative xy times this guy, derivative with respect to x, which is what? Another negative 2x. Then you subtract this guy times the derivative of this with respect to y. And then you add this guy. And we'll do an r drd theta version. So 0 to pi upon 2, 0 to 1. You multiply this out and you get positive 2x squared y. You multiply this out and you get positive 2y squared z. And then you have a z x. I'm taking this nice and slowly. What I'm going to do next is replace the z's with this, and then turn everybody into r's and thetas after that. So I have 2x squared y plus 2y squared, all of this, plus all of this times x. Or dr d theta. Depends going on me here. So I have a 2x squared y, 2y squared minus 2x squared y squared minus 2y to the 4 plus an x, take away an x cubed, take away a y squared x, or dr d theta. Switch bends. Anything here going to kill anything here? Because I don't think so. Anything combine even? Oh, come on, you should have something. I get absolutely nothing. Absolutely nothing. So isn't x going to be r cos theta? And won't be y r sine theta? Why are all my pens going? Plus I'm dotting this because this is going to be just ridiculous. Would you agree that you're just going to get all sorts of combinations of r's and cos squareds and sine squareds? And aren't you just going to have to do probably quite a lot of u subs? And 20 minutes later, you're going to have 42 pi or something when you're finished. I am not convinced that this question is that short. And the only reason you would need to do this process would be if the integral was easier to do, which I don't think this is, or that this would just be impossible to do. Can you imagine that there's just some line curves that you can't do in the usual way, right? The integrals just don't come out. So I guess it has to be that second one. My dog is trying to make her presence known. But we got other things to do, so poor thing's outside. She'll now go to my wife and bug her, and she'll have to take him out. So, yeah, so that's her. She's trying to make her presence known. So I'm a little bit disappointed in that one. I think the textbook could have at least picked one that would have solved a lot nicer or quicker than the one we just did. What the heck was that? That was 11, wasn't it? Okay. I'm going to mute people because we do not need to hear their conversations. Okay, that's it. Any questions about that one, apart from the fact it's downright ugly and it'll take you forever? No, you're just going to live with that one. I'm hoping that the next one that I've picked will come out a lot cleaner. And it will. Here we go. Here's our vector function. Or the curve C is the intersection of this plane and this cylinder. So this is the plane. I already know who g of xy is. If you take a cylinder, which would basically be a vertical cylinder going up the way, can you imagine it being cut with a diagonal plane? When you project that down into the floor, isn't d just x squared plus y squared equals 1? Can you imagine a vertical cylinder being cut by a diagonal plane? Right. The surface might look like an ellipse, which it does, but won't you see d on the floor as just being a circle? Right. And so the circle is this guy with a radius of 1. So we have 0 to 1 and 0 to 2 pi. Now you can't get much nicer than those two. And would you agree that P, Q, and R are pretty much freebies? You don't really need to work to get P, Q, and R. Well, that was cool, right? There's the region D. That's what the cylinder would look like if you saw it on the floor. Okay, so this line curve. Got all the information here. Let's get to use it. It's going to be the integral from theta equals 0 to 2 pi, from r equals 0 to 1, negative 8y times this derivative here with respect to x, which is 0. That's nice. Q is xz times the derivative of this with respect to y is 1, plus r, which is xy. And we're going to go polar. So r dr d theta.
Is r xy or x plus y?
Well caught. X plus 1. This guy's nothing. This guy is negative xz. And this guy's still x add y. And you do not need all these lines, but I'm putting them in because I'm careless. Plus, when you go back to watch the video, I'm hoping that you do, if you get stuck at least, you'll see every line that I could possibly think of. Right, now, let's take this just a little bit further because I think it's at least doable. Negative r cos theta r sin theta. Take away 8 r cos thetas. Oh, wait a minute. Wouldn't that get you negative 7? Negative 8x plus that. So why don't I stick that together? That's one less thing to do. And 7 sin thetas. Or dr d theta. So,
Mr. Robertson,
yes,
you wouldn't have 7r sine theta. You just have sine theta.
thank you. Even doing it carefully, my dog is scratching the heck out of my door right now. So as soon as I finish this, I'm going to see if we can get my wife to take over. Because oh, times r. Give that an extra r. Give that an extra r. Give that an r. And now I can do dr d theta. Okay, can you imagine that that's at least doable? And that's going to be a u sub. That's just going to be a version of sine theta. That's going to be a version of negative. That little mess in there is I forgot that everybody gets an r. And dot, 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 dot. Okay, I guess this is going to be the last one. So this is like 14. Here's our vector function, so we already know who P, Q, and R are. Oh, wait a minute, I don't need to do this one. Isn't this one virtually the same as the one I did a minute ago? Yeah, let's not do that one then. Let's do the other one. A little different, but same old, same old. Right. I have a P, I have a Q, I have an R. I can handle that. This here is the plane. So you tell me that's the plane. That guy is going to tell me G.
Should we do roll?
Good idea. Why don't you say hi right now while I'm setting this up? So I found out who the equation of the surface is. It's just basically negative x, negative a half y. I got this fella up here. If you want to take this fella and you project it onto the ground, do you see that what you end up with is 2x plus y equals 0, because you make z 0. And you get 2x plus y 0, which a quick rearrangement is what, negative 2x? And why am I doing that? Oh, sorry, that thing there distracted me. I was looking at my x squared plus y squared and didn't realize that I had changed the question on us. So what's this guy going to look like on the floor? Oh, that explains something. My apologies. That's actually a 2. There we go. I was wondering why that didn't work on the first quadrant. The reason it didn't work on the first quadrant is I forgot to take this fella with a 2. So,
Mr. Robertson,
Yes.
So in the third line where you have it circled, shouldn't that 2 be 1 because you divided everything in that equation by 2?
That sounds very plausible. So that 2 becomes a 1. Okay. Right, look, take that as if I hadn't done it before. This is the correct plane. And you subtract those guys and you divide it, you get that. So that is the g of xy that I'm making a big meal out of. Now you take this guy and you find out what does he look like on the ground in the first octant. And basically you make this 0, and what you're looking at is 1 take away x, take away a half y, I guess equals 0, right? Now if I rearrange that a little bit, I should be able to get the equation of a line. And let's see what we have. Well, if I double everything, it's probably going to make my life easier, because it's going to make y equal 2 minus 2x, which basically makes it that guy. So I now have my region D, and my region D is going to be x equals 0 to 1, and y is going to be from there to there. So I got my D, I got my G, I got my PQR. So I should be pretty much ready to go then. So this line integral has the same value as this double integral. And we are going to be using x from 0 to 1. We're going to use y is 0 to 2 take away 2x. And then we're going to do the negative of this ugly guy times the derivative of my g with respect to x, which is just negative 1. Then we're going to subtract this fella, and he's going to be dg by dy. And if you differentiate this guy with respect to y, you get negative a half. And then you're going to have an e to the z, which is going to be this guy, dy dx. I'll just tidy up a little bit. You're going from 0 to 1, from 0 to 2 minus 2x, e to the negative x, plus 1/2 e to the x, plus e to the 1 minus x, take away a half y, dy dx. Are we comfortable about that just being a ... question now? Right. So that is it.